see if I can hit a mic at some point, but
not that critical, as long as I remember. This works fine for me. I don't know if it works that good for you or not. I don't know what the audio is like, but this is fine for me. So, what are we doing tonight?
So tomorrow I have a test. I got a review here.
Okay.
Basically, one of them is like two sheets here. One sheet just the quiz that we had a while back.
Okay.
And then the other one is
we can go over whatever you'd like to go over. We got an hour, so.
All right.
I'll let you call the shots.
Okay, so this one says, find the length of an arc circle with a diameter of 17 centimeters intercepted by a central angle of 114 degrees. And it says to show the equation.
You said the diameter was what?
17 centimeters.
7?
17.
17, and that's a diameter?
Yeah.
So that means the radius is 8.5. Is this trig?
Yeah.
Okay. In trig, the length of this arc is equal to 2 pi times, hold on a second.
I mean, the equation that I have here, which I'm not sure if it's right, is S equals R theta.
No, that's perfectly right, as long as theta is in radians. That's right.
Okay.
Okay. In other words, yeah, theta can't be in degrees. If it's in degrees, then it's r theta times pi over 180. Let's see if that would be right. If this was 360, that would be the whole circle, whose circumference would be 2 pi r, and that's what I would get. So those are your two formulas, depending on whether you're in degrees or radians. So this becomes relatively easy. It's S equals 8.5 times 114 times pi over 180. That's the arc length. Now, the reason I asked if it was trig, or I remembered that it was trig, requiring these formulas, this is actually a problem that you can figure out geometry-wise also. Let me just show you real quick. I don't know if it'll help your understanding of it or not, but notice that this arc length has to be 114 over 360 percentage of the full circumference.
Okay.
See where I get that?
Yeah.
Just like this sector area is 114 over 360 times pi r squared. In other words, if you can figure out the area of the full circle or the arc length of the full circle, which is the circumference, then the segments or arc are merely the percentage of this circle. In other words, this segment here is 114 divided by 360 of that circle. Whether it's the area or the circumference, it's that. And what that produces is these two formulas. If you're in radians, it's in that. Otherwise, it's that. And that's easy enough because you know pi over 180 is the conversion factor to go from radians to degrees, or degrees to radians.
Yeah.
All right. So these formulas make these calculations actually quite a bit easier. You got another one?
Yeah, so there's a section here where we have to find, just to approximate the value of each of the following. So we were allowed to use calculators on this one, but
Okay.
I wasn't sure if I could do secant and cotangent. I wasn't,
Okay.
like, there's not that, so.
What kind of, you got a TI 84?
Yeah.
There's only 3 keys on there for trig functions: sine, cosine, and tangent. The other 3 trig functions are the reciprocal. So what's your first problem, and then I'll show you how to do it on this calculator.
Secant of 49 degrees.
If I take 1 divided by the cosine of 49 degrees, that's the secant of 49 degrees. In other words, that is equal to the secant of 49 degrees. So that's the way you have to do them, is you have to do 1 divided by cosine of 49. And make sure I'm in degree mode. I am. Okay? It's as straightforward as that. As long as you know the reciprocal, that's the way to do it.
Would it be the same with cotangent and cosecant?
Yep. So cotangent of 49 degrees would be 1 over the tangent of 49 degrees. It's why they don't put the 3 other keys on there, is because it's too easy to do it this way, by taking the reciprocal. I think one of these keys is even a reciprocal key. That's not the way I did it. I did 1 divided by it, but it works.
Alright.
If you had an Inspire, the new Inspire actually has all 6 trig functions on there. They've got a key that says trig, you hit it, and it gives you a choice of all 6 trig functions. So you don't have to do that reciprocal bit. But this works just as well.
Okay, the next one is use a reference triangle to find theta for each of the following.
Okay.
Give in both degrees and radians, and it has to be exact answers, so we can't use a calculator.
Okay.
The first one is cotangent theta equals 1.
Okay. If the cotangent of theta equals 1, what's the tangent of theta equal?
Would that also just be 1?
It's 1 over cotangent. So if I plug in 1 for that, then the tangent of theta is also equal to 1. 1 is the only number whose reciprocal is the same thing. So on anything that's equal to 1, both the reciprocal and that trig function are equal to 1. So the question is where does this occur? Where is the tangent of theta equal to 1? And you can't use your calculator, so we want to use these two triangles again. Which angle is the tangent equal to 1?
That would be 45.
Correct. So theta equals 45 degrees. What is that in radians?
Pi over 4.
Uh-huh. Notice that that times that's always equal to 180. As long as it's pi in the numerator, not 2 pi or something. But that's a real easy way to do a conversion of these small angles, is to always know that the denominator of this times that's equal to 180. So that pi over 6 has to be 30 degrees because 30 times 6 is 180. Pi over 3 has to be 60 degrees because 30 times 6 is 180. Just a good little thing to remember for converting your small angles. Okay, I'll leave those triangles up there. What another one?
Another one, secant theta equals 2.
God, I knew that that was going to be the problem. I just knew it. I was going to read that to you without seeing it, because that's the one I would have given you. So if secant of theta is equal to 2, what else is secant of theta equal? 1 over what?
1 over 2?
No, what's the
1 over cosine 2?
No, just 1 over cosine of theta. In other words, secant of theta is equal to 1 over cosine of theta. So here's the equation I'm going to solve. So therefore, cosine of theta is equal to 1/2, right?
Yeah.
What angle is the cosine of theta equal to 1/2?
30.
Remember, cosine is adjacent over hypotenuse.
Oh, okay, so 60.
Right. And that's key. In other words, the sine of 30 is equal to 1/2. That means the cosine of 60 is always equal to 1/2. There's that relationship. The sine of an angle is equal to the cosine of 90 degrees minus that angle. Always. All of the cofunctions have that relationship. And the cofunctions are sine, cosine are cofunctions. Tangent, cotangent are cofunctions. And secant, cosecant are cofunctions. In other words, to get the cofunction, you just stick the word co in front of it. Okay? And this is worth knowing, because most everybody comes to memorize that the sine of 30 degrees is 1/2. So if you're coming up with the cosine of 30 degrees is 1/2, that can't be right. So the cosine of 60 degrees is equal to 1/2. So that's the way I do all of these. You wouldn't necessarily have to do that one that way. Let's go back and look at that. Secant of theta equals 2. The way I did it was converted it to cosine, right? But you don't have to. Secant is hypotenuse over adjacent, because it's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant must be hypotenuse over adjacent. Well, to get 2, there's the hypotenuse over the adjacent. The answer's got to be 60 degrees. So I don't have to convert everything to one of those 3 primary angles. you can get to a point where you can do it direct, just like I just did it. If I said to you the cosecant of theta equals 2 over root 3, what's theta?
Is it 30 or?
No, it's 60. In other words, the sine is the reciprocal, right? Sine, SOHCAHTOA, sine is opposite over hypotenuse, so cosecant must be hypotenuse over opposite. Okay? Instead of opposite over hypotenuse, it's the hypotenuse over the opposite. Well, I said 2 over root 3. Well, there's the hypotenuse. The opposite is root 3. Therefore, we must be talking about that 60-degree angle. And I kind of did it without translating it to sine. I'm not saying that that's the way you want to do it. Probably the easiest thing to do is to say sine of theta is the reciprocal of that, which is root 3 over 2, and now it's easy enough to figure out that that's 60 degrees, opposite over hypotenuse. So you can do it either way. I've always done it this way, just because in my mind there are 3 primary trig functions, sine, cosine, and tangent, and there are 3 secondary trig functions. And I've always thought primary mode. I pretty much take everything and convert it to one of the 3 primary ones. Even though you don't really need to do that, and there's nothing more primary about the first 3 than there are the second 3. They're every bit as legitimate and primary. All 6 of them are primary functions, if you know what I'm saying.
Yeah.
It's just a little easier to think in terms of 3 trig functions than it is to think in terms of 6 trig functions. I don't know how long SOHCAHTOA would be if you had to include all 6 trig functions. It would be SOHCAHTOA and then something that starts with a C and an S and a C again. So, all right, what else you got?
It says consider a wheel radius 3 feet rotating at 400 RPM round to the plate and determine the angular speed in radians per second of the wheel.
What's the radius again?
3 feet.
And that's a radius, not a diameter?
Yeah.
Okay.
At 450 RPM.
Determine the angular speed of the wheel.
Yeah.
It's making 450 rotations per minute.
Yeah.
Well,
I'm not sure if these are it's yet, but the next part we will.
that is 7.5 rotations per second. Let me open my trig book. This problem, for some reason, gets me every year. And I think the solution is to just use all of your conversion factors, right?
Yeah.
Yeah. Yeah. Hold on a second. I know how to do this. Using angular speed. Okay. 450 revs per minute times 60 minutes per hour times 2 pi radians. This is the key part that I always have trouble with. Per rev. In other words, converting it to radians. Okay. Now, we've got 8 inches, or in our case, a radian is the radius, right? So it's 36 inches per radian. Notice what's happening here. Times 1 foot per 12 inches times 1 mile per 5280. Notice that my minutes cancel, my revs cancel, my radians cancel, my inches cancel, my feet cancel. Where's my other foot? Right here, that's the foot. So my feet cancel, and I end up with miles per hour. So the answer is 450 times 60 times 2 pi. I'm sorry?
It's supposed to get it into radians per second, not miles per hour.
Oh, okay. Well, there's miles per hour. Okay. So to get it into radians per second, we just have to use some different conversion factors. Let's see. Where did our... We want radians per second, so we don't need any of this stuff. But we do need 1 minute per 60 seconds. Now the minutes cancel, the revs cancel, and I end up with radians per second. 900 pi radians per second. That's the way you do those problems, is you use whatever conversion factors are necessary to get it into the final thing. In other words, we start out with revolutions per minute. We just have to use the correct conversion factors to convert that to radians per second. Okay? And that's that's the only angular motion problem anybody ever gives me. And the real key to remember is this part right here. The 2 pi radians per revolution.
Wasn't that part with 1 minute over the second?
Oh, yeah, 60. There's a 60 seconds there. So I got to divide that whole thing by 60. So it's actually 15 pi radians per second. Yeah, thank you. And that's a good thing to check, is make sure all your conversion factors are correct.
Right. Then I have one for linear speed in miles per hour. So I guess we have that one earlier.
Let's see. If I'm doing 15, actually that was the angular speed in miles per hour.
Oh.
If this is the angular speed I think angular speed times radius gives you linear speed, does it not?
I'm not sure.
Pretty sure. In other words, if I multiply this by 3 feet, that should give me feet per second, and then I have to multiply it by, hold on, linear motion. Linear speed it doesn't tell me how to get linear speed, but let's see. Linear speed is, yeah, angular speed times, in other words, how fast, if this whole thing is going around at 15 pi radians per second, what is this point doing? In other words, what is a point on the wheel doing?
Going around 15 5 times? Or?
Well, every second, this thing is rotating 7 times, 7.5 times, right? Every rotation is 2 pi. So this thing is doing 7.5 rotations a second. So let's start there. 7.5 revolutions per second. Every time it makes a revolution, this point travels a distance of the circumference. In other words, 2 pi r. So it's 2 pi times 3 feet per revolution. The revs cancel and you end up with 42, well, some number pi feet per second, which is a linear speed. Okay? Our angular speed was radians per second. But our linear speed, in other words, if these were the tires on a truck, it would be going this speed. If it's making 7.5 revolutions per second, well, every time it makes a revolution, it travels a circumference forward. Right? If I turn that tire around 1 time, then it's making 6 pi movement laterally. If you had 4 wheels on a car and every one of them rotated exactly once, the car is going to go forwards by 6 pi feet, the size of that circumference. Well, these wheels are rotating 7.5 revolutions per second. So I'm going to multiply that by 2 pi r, the circumference. Here's 2 pi r times 7.5. That gives you its linear speed in feet per second. To convert it to miles per hour, just use all of the conversion factors that we were talking about. In other words, once you get it in feet per second, it's pretty easy to get it in miles per hour. Here, let's do it real quick. So this looks to me, 2 times that's 15 times 3. So this is 45 per second. So what else do I need to multiply to get this to miles per hour? If I want to end up with miles per hour, give me all my conversion factors.
The 5280 feet in a mile.
But I don't want the 5280 feet up here because then the feet won't disappear.
We'll go in the denominator.
It's got to be 1 mile per 5280 feet. That's how you decide whether it's the reverse or not, is we're trying to get the units to go away. Okay, so now I'm in miles per second.
Then we'll do 3,600.
Seconds per hour. Okay, now the feet cancels, the seconds cancel, and I'm left with miles per hour. So my final answer has to be 45 times 3,600 divided by 5280. And that'll be miles per hour. Looks like about 30 miles an hour, maybe. Somewhere in that ballpark. And that might be a question you would get, which would be a variation on that question. It would tell you you have a car that has 4 wheels on it, and they're each turning so many revolutions per second. How fast is the car going? The car is going the linear speed of the outside of that wheel. So that's all you need to remember, is if you can calculate the linear speed of a point on the circumference of that wheel, that's the speed the car is going.
Alright.
And that's why bigger wheels can go faster. Notice that if I have 2 wheels, and I have one car that's got these wheels and another car that's got these wheels, and both wheels are rotating at, say, 10 revolutions per minute, this car is going to go faster, quite a bit faster. Because every time this car makes a revolution, it goes the circumference of that circle. That's how far it goes. So if they're both making 1 revolution, say, per second, well, this one's going much bigger circumference. That goes further than this one. Or I should say faster. Are you just starting Trig?
I took Trig last year, and now I'm in the honors Trig class.
Okay. But you didn't have it last semester, right? You had the pre-calc part last semester? Because these questions that you're giving me on Trig are the first chapter of every Trig course.
Yeah, these are the ones that I've been missing.
Well, it might be the hardest part of Trig, to be honest. Of all the Trig, I find the first chapter to be the hardest. I don't know why math insists upon doing that. They do the same thing in geometry. They start you out with proofs. And if proofs aren't the hardest part of geometry, I don't know what is. And when they go to calculus, they start you out with the limit definition for derivatives, and that's one of the hardest things there is. They don't believe in starting you off with easy and working to difficult, I guess, which is my philosophy of teaching. You should start off with easy and work to difficult. But yeah, this first chapter of Trig is as confusing as it gets. I mean, I think I finally understand it. partly what happens for me is that when I pick up a student, it's usually after they've gotten through the first couple chapters and they run into difficulty, and so they call me and bring me in, and so I don't ever have to do the first chapter with most of my trig students. Just like I get to skip the proofs in geometry, because I don't get called in until after the first month, and then they're beyond proofs. What else you got? I think I can probably figure it out.
Yeah, so this is the review that a couple of days ago. The first one I didn't get was let theta be an angle in standard position. Let quadrant contain the terminal side of theta if secant theta is less than 0 and tangent theta is greater than 0.
Okay, those two conditions right there give you the quadrant. Where is that true? Where is the secant less than 0 and the tangent greater than 0?
That would be the third quadrant.
Uh-huh.
Okay.
And that's all it wanted, was you to spot the quadrant?
Yeah, I was kind of confused by the wording the first time, but...
Yep. As long as you remember this, all students take calculus.
Yeah, that's what I just had to remember.
Okay.
I just didn't really understand the wording until I read it out loud, I guess.
Uh-huh. All right.
Okay, this one is let theta be an angle in standard position with p equals 6, -8, that goes the coordinate, on the terminal side of theta, and find each of the following. To find cosine theta and tangent theta.
Okay. What quadrant are we in?
The fourth.
Okay. Now, the angle they're talking about is that angle, but we can analyze it from the reference angle. In other words, by analyzing this triangle right here, we're going to be able to figure out everything we need. There's theta. Theta is the angle made with the x-axis, no matter what quadrant you're in.
All right.
Okay. Well, that side's 6, that side's 8. What's the hypotenuse?
So it would be 64 plus 36.
That's a 3, 4, 5 triangle.
Okay.
You want to speed things up if you recognize that that's a 3, 4, 5 triangle immediately. Then you don't have to use the Pythagorean theorem to solve it. Okay, now what do they want to know?
The cosine of theta and the tangent of theta.
Okay, what's the cosine of theta equal?
So that's adjacent over hypotenuse, so 6 over 10, 3 over 5.
Okay, and it's positive. And there's a couple of ways you can put the plus or minus sign on it. You can come up with the number based on this triangle and then put the plus or minus sign on it based on all students take calculus. Or you can see that this is actually a plus 6 and this is a negative 8. So I could just use the signs of these things to come up with the sign. The hypotenuse is always positive. The unit circle is actually your first exposure to polar coordinates. And in polar coordinates, it's always positive. In other words, it doesn't matter what quadrant I'm in. This 10 is a positive 10. Okay. So if I go to figure out the cosine of theta, it's a plus 6 over a plus 10. And that's how I get the plus 3/5. If I go to figure out the tangent of theta, it's a minus 8 over a plus 6, or a minus 4/3. Now the other way would just be to ignore the signs, figure out that it's 4/3, and then realize that it's in the fourth quadrant, so it has to be negative. Either way works, and either way always produces the same answer. I'm actually a little partial to figuring out the number and then putting the sign on it. I actually think that that probably gives you less chance of error. In other words, if I attach these signs like that and do it, I think there's a greater chance of me getting the sign wrong than if I just do 8 over 6 to get 4/3 and then realize that tangent's negative in the fourth quadrant, so it has to be negative. You know what I'm saying?
Yeah.
But either way works. Okay. Got another one similar to that?
That was the only one for
Okay.
that.
Yeah, no, that's fine. Or whatever you want. Incidentally, let me just bring this up. Let's say I had that. No, let's say I had this. And I'm on the unit circle. The cosine of theta on the unit circle is always equal to the x-coordinate. The sine of theta on the unit circle is always equal to the y-coordinate. So if I wanted the cosine of theta, I can read it directly. It's 0.6, which, remember, that's what we came up with, 3/5. And the sine of theta is 0.8. In the case that we were looking at, where we had 10 as the hypotenuse, and this point was 6 comma minus 8, we could just divide everything by 10 to reproduce the unit circle. So if the hypotenuse was only 1, then this would be 0.6, and that would be negative 0.8, and I could read my cosine and sine directly off the coordinates. The cosine is always the x-coordinate, the sine is always the y-coordinate. Okay, and to understand why that's the case, let's look at this triangle here. Sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to the adjacent over hypotenuse. Notice the sine of theta is equal to the y-coordinate, the cosine of theta is equal to the x-coordinate. As long as your hypotenuse is 1, which it is on the unit circle. So when you get to studying the unit circle, they will want you to know that. Okay.
So this next one has, like, it just doesn't equate.
Okay.
And it wants to find the
Okay.
all that. So it's 2 sine parenthesis pi over 2x minus pi over 2 and parenthesis and plus 3.
What's the amplitude?
2.
What's b?
That pi over 2.
What's the period?
That's 2 pi over 2. Will the pi's cancel out there?
Uh-huh. And you get 4.
Okay.
In other words, if you flip the bottom and multiply, pi's cancel, 2 times 2 is 4. So the period is 4. You call this letter H and K?
Yeah.
What's H?
So if we divide the pi over 2 out, like if we factor that out, would that make it 1?
Yes. Well, H is pi over 2, but the phase shift becomes 1.
Okay.
Because you're correct. This has to be on the outside of the parentheses before I can't say that that's the phase shift. The phase shift is only after I've turned it into this. Now I can say that that 1 is the phase shift. So it depends on how you get the sinusoid function. And it's very critical to recognize whether your coefficient of x is inside or outside the parentheses. And k is plus 3, meaning what?
Get the vertical shift up 3.
Yep. And what's the horizontal shift? In other words, what's the phase shift? 1 in which direction?
To the right.
Yep. Okay.
Then it wants a sketch of the graph.
Okay.
Oh,
Let's graph it.
yeah.
What's the first thing I'm going to do to graph it?
Find the period.
You know, the first
Like
thing
where-
I do is to do the k, because there's my new line of symmetry that I'm going to graph everything about. By the line of symmetry, I mean that's like the x-axis.
Yeah.
Okay? And that's at 3. Where's my high point and where's my low point?
High point will be at 5, and low point at 1.
Okay? So I'm going to graph it in this area. Where is my starting point?
At 1.
Where's my ending point?
5.
Okay? And I'm graphing the sine. So it starts right here, ends right there. Got to go up and hit my high point right there. Got to come back down through the axis right there, hit my low point right there, come back to there. So the curve looks something. There is one period of the curve, and of course if I continue drawing it, it's going to In other words, I don't know if they let you get away with, do they let you get away with just drawing one period?
Yeah.
Yeah, they should. They shouldn't make you finish drawing it. If it's the reverse, they may show you a picture that looks like this and forces you to calculate everything, and then you have to figure out the period on your own. But, yeah, that's the way to do that.
Okay.
Okay. What else? Got another sinusoid?
Okay, this one, use a right triangle to determine the exact of all the trig functions.
Okay.
Theta.
Which one?
Cotangent theta equals 11 over 3.
They tell you which quadrant it's in?
Well, it's not like negative. Would that matter? Or?
It will, actually. Let's assume first quadrant. Okay. Start by drawing the right triangle and labeling theta. Both of them are very important. If you don't label theta, you can't start dimensioning the triangle. By knowing that the cotangent of theta is 11 over 3, I can dimension two of the sides of this triangle. Which two?
The side opposite of it and adjacent.
Since the tangent is opposite over adjacent, the cotangent is adjacent over opposite. So this has to be the picture. Okay? Now I can put the third dimension on that. And all of these type problems, this is exactly the way you do all of them. So what's this equal to? Square root of 130, I guess?
Yeah.
Okay. Now notice I can give you all 6 trig functions of theta, because I know all 3 dimensions. And that's where the quadrant matters. In other words, if it's first quadrant, then all the other 5 trig functions are going to be positive. If it's, say, second quadrant, the numbers are all going to be the same. Let's do it for second quadrant. What's sine of theta? And notice I don't ever figure out what theta is. I don't know what theta is. I don't care. What's sine of theta?
That would be 3 over root 130.
Yeah, let's not worry about rationalizing it at the moment. Is that a plus or minus in front of it?
That would be a plus.
Okay, what's cosine of theta?
That would be 11 over root 130.
What's the plus or minus sign on that?
Negative.
What's the tangent of theta?
3 over 11.
Okay, well, I made a mistake here. I arbitrarily put it in the second quadrant, and it can't be in the second quadrant because cotangent's positive. So let me go back and say third quadrant.
Oh, okay.
Okay? So if it's third quadrant, cotangent would still be positive, so that's okay. Sine's going to be negative. Cosine's still negative. Tangent's positive. In other words, all the reciprocal functions maintain the same sign.
Okay.
Okay, if sine is positive, cosecant is positive. If cosine is negative, secant is negative, and so forth and so on. So let's do the last two. What's secant of theta?
Root 130 over 3, so that would be negative.
Over 11. Secant is reciprocal of cosine.
Oh, okay.
Okay? And finally, cosecant?
So that one would be the root 130 over 3.
Let me just show you something real quick so you'll never mix them up. There's our three primaries. I know this one, right?
Yeah.
The only thing I have to figure out is whether secant goes with sine or does it go with cosine. Every one of these pairs has a co in it. That's the way you can always tell. There's the co there, there's the co there, and there's the co there. In other words, cosecant or secant can't go with sine. There's no co in it.
Okay.
Okay? Now, having said that, these are not cofunctions of one another. Cofunctions, sine, cosine, tangent, cotangent, secant, cosecant. Those are cofunctions. And cofunctions share the property that the sine of theta is always equal to 90 degrees minus the cosine of theta. For all three of these relationships. Hold on a second. I made a mistake here somewhere. All of a sudden I just drew a blank. So the sine of 30 degrees is 1/2, and it's the same as, it's not 90 degrees minus root 3 over 2. I wrote it wrong. It's equal to the cosine, the cofunction of 90 degrees minus theta. There's the cofunction relationships. And vice versa. In other words, also, cosine of theta is equal to the sine of 90 degrees minus theta. In other words, if theta were 30 degrees, sine of 30 degrees is 1/2, and cosine of 90 minus 30 is cosine of 60, that's also 1/2. So these cofunction relationships are always like this. Okay? But that's cofunction. These are not cofunction. It's just a little memory tool I use to memorize whether the cosecant goes with the sine or whether it goes with the cosine as a reciprocal. Every one of these reciprocal pairs has one co in it, and that helps you memorize it so that you don't ever make the mistake. But don't mistake that for the definition of cofunctions. All right. You good to go for this evening?
Yeah.
All right, Daniel. I will talk to you next time.
All right. I did send a check in the mail for you.
Okay.
That,
Thank you.
cover last week and this week as well.
Okay. Sounds good. Thank you very much. I'll talk to you next time.
All right. Bye.
Bye-bye.